There have been several attempts to develop programs which will analyze programs or analyze code and suggest to programmers where parallel programming would best be implemented. There have also been attempts to build this capability into compilers themselves. Here we talk about just a few of the more recent projects, the more recent research which has been done. One research project called Triple P does just what we've talked about. It uses synthesis to compile at compile time to generate parallel binaries from declarative programs. It abstracts the execution order of the program away from the developer and allows for explicitly parallelism without requiring architecture-specific annotations and structures. Parallelization of programming is such an important area of research that back in 2001, DARPA challenged companies and industries alike to develop new parallel languages and programming tools. Another model called the PP model helps separate out sequential and parallel parts of a program into blocks without modifying the code. Also, we come to Marple. This was developed to help businesses automatically migrate their legacy software systems and data parallel platforms like the NVIDIA to a data parallel platform like the NVIDIA CUDA GPU. In conclusion, parallel program may always be an issue for software developers that software developers have to contend with. However, there has been a lot of effort devoted to automating the job of spreading tasks across several threads and several processors. The work has mainly focused on improving the compiler as well as develop an intermediate software which would analyze the code, which will seek out areas ideal for parallel processing. So currently you kind of have the software developers, the ones in high-level programming languages, having to think really heavily about parallel programming and how to break down their code. It'd be nice, and what computer science industry is working towards is trying to separate out parallel programming and software design. They would like to get some of the parallel programming have the languages themselves take care of trying to figure out what parts of code would be best in parallel processing. And you also see a new line of analyzers, of code analyzers, right along here that before the code actually gets compiled, you would run them through these program analyzers, and the program analyzer would tell you or suggest to you which code would be best implemented in parallel form and which ones are best for series. One of the easier hurdles to overcome is a battle between the CPU and GPU industry. Market demands as well as global demands will encourage the progress of technology. Along with this, mergers such as the merge between AMD and ATI will hopefully alleviate the tensions and encourage teamwork to create an ideal processor. Another sector which will help alleviate these tensions between the GPU and CPU companies are the partially non-biased middle people such as vendors and government. Vendors such as IBM, Dell, HP, etc. realize the need for GPUs, both GPUs and CPUs. They help facilitate the creation of heterogeneous systems. As far as the government being a middleman person, you saw back in 2010, NVIDIA and Intel are working together with DARPA in something called the Exascale Computing Project. And this was kicked off to try to create a faster, more efficient processor. And then back in July 2012, you saw NVIDIA, Intel, AMD, and WEM Cloud start working together with the Department of Energy on a program called Fast Forward Exascale Computing, and this also had to deal with creating a processor which took advantage of the GPU processing capabilities as well as CPU capabilities to make the ultimate most efficient processor possible. For these reasons, truly heterogeneous machines may actually be achievable without the intimate relationship and sharing of proprietary information between CPU and GPU companies. In conclusion, we shouldn't really expect or hope for the separate companies to play friendly. We're always going to have lawsuits and fighting. The main concern for the public is that the bickering between companies doesn't infringe on the overall progress of their computing technology, but instead encourages its growth. No one nowadays really disputes over the need for hybrid computing. The main disputes comes when the companies try to decide which processor should do which tasks. So the next hurdle we're going to talk about is the complexity of current GPU program APIs and architecture. Now, a lot of the complexity of the GPU program APIs is due to the complexity which comes along with parallel programming. GPU programming can be fairly complex and error-prone. Several methods of improvement have been suggested from the research community. So in order to lessen the complexity of GPU programming, we first need to improve the ease of parallel programming. Also, parallel program readability still needs a lot of work. It tends to be more difficult for humans to conceptualize since it's more natural for us to think in series. Our lives occur in chronological or serial order. We also need to work on creating a higher level of programming abstraction, similar to what you see in stream programming models. Running code for the GPU is still a ways off from being highly efficient as well. You see it evolving in CUDA with the compatibility with C++ programming, but Java, when it comes to programming GPUs in Java and other high-level programming languages, you still are quite a ways off from having a good program interface. So this picture is just to explain the situation in a dramatized manner. It shows a scenario in which could happen if we don't continue to work towards improving GPU interface, the GPU APIs and GPU architecture complexity. So let's pretend you have DeWalt, someone from a company that sells tools, and they come to Patran. Patran is a company who develops structural software for analyzing structural analysis. So you have these people from DeWalt saying, "Hi Patran, I need a fast structural analysis tool." And then Patran's like, "Okay, that'll be about 2 years. Wait, we have to learn the latest GPU hardware and libraries and write the code for that specific GPU. And then you must," talking to DeWalt, "you must also purchase along with the software, the specific GPU for the software. And then when you upgrade your hardware, you also must update the software to take maximum advantage of the hardware. So you'll have to contact us again." And so then, of course, that kind of makes the people in DeWalt, or the people who actually manufacture the tools and use the software, not happy. And then when the little consultant for Patran goes back to the software engineer and says, "Okay, we need to develop software and we're going to use the GPU programming to do all this so we can make a really super fast structural analysis tool," then you have the little software engineer, and he has to look at all the books and try to figure out how to program on the GPU chip, and has to actually learn a little about the hardware to figure out how to program on the chip, and it just becomes somewhat complex task. And this can be simplified a lot, and there has been a lot of research done to improve this whole process. Okay, so the last hurdle to talk about is the lack of portability when it comes to GPU programs. There are several technologies which have been developed to help enable portability of the GPU programs. One of these architectures is called the OpenCL architecture. This architecture was initially developed by Apple in 2001 and later handed over to Khronos. Khronos is a nonprofit member-funded industry consortium which is comprised of roughly 100 members. Some of the Khronos company members are companies such as ATI, Discrete, Evans and Sutherland, Intel Corporation, NVIDIA, SGI, Sun Microsystems, etc., etc. So OpenCL can be implemented on a number of platforms, including cell phones, which is a great feature of OpenCL, which you don't see in a lot of other GPU APIs. When the GPU hardware is not present, this OpenCL can fall back on the CPU to perform the specific work, which is also a plus. OpenCL supports synchronization over multiple devices, and it's fairly easy to learn. Another good thing about OpenCL is that it shares resources with OpenGL, another product of the Khronos group. One of the best features about OpenCL is that, unlike others such as CUDA, it can work on numerous GPU brands, including NVIDIA, ATI, Ivy Bridge, and others. So besides for the OpenCL, around 2009, Microsoft came out with something called Direct Compute, and this eventually got replaced by another Microsoft product called C++ AMP, which builds directly on Direct Compute, and I think it's supposed to be similar in nature to OpenCL, just that it's not open source and not built by a consortium but by an individual software company. You also see research being done on GPU code portability in universities. One type of project of this type was called Sponge. This was a compilation framework for NVIDIA GPUs which use synchronous data flow streaming languages. The accomplishments of Sponge were that it abstracted the details for the hardware. It also created a write-once optimization CUDA code for a variety of GPU targets. It also would take care of the GPU to host, or GPU to CPU, and host to GPU communication. It did attempt to determine what sections of the code would be better suited for the GPU and which parts of the code would be better suited for the CPU. In the end, by using the Sponge Sponge program, they saw performance improvements rise to about 3.2 times that of the original GPU baseline benchmark code. So when it comes to conquering the hurdle of the hybrid heterogeneous computing, overall, this really requires us to solve some of the other hurdles that we've previously talked about. And once we solve those, then you'll slowly see some of the problems that come along with hybrid computing also untangle. Some of the progress in streamlining hybrid computing is producing software that can support hybrid computing, such as OpenCL, and generates code that can run on GPU, on all different types of GPU CPU combinations. It can run on multiple GPUs. If you don't have a GPU, it can fall back on the CPU, and this is a real plus and something which we need to see in all types of hybrid computing languages. Also, we still have to tackle parallelization in order to really see hybrid computing through to its fullest. Hybrid analyzers would help to aid in process distribution amongst the GPU and CPU as well.